Okay, so this is a question that's talking about roots of unity. So just to remind you about what roots of unity is, it's helping us find all of the different solutions on the unit circle for this. So here I've got w to the power of 3 equals 1, meaning that there are 3 solutions for this complex number. The imaginary component of it must be greater than 0. Then it's telling us that we have a different polynomial like this, and it has roots at 1, negative whatever our answer was from up here, and negative of the conjugate of whatever's up here. Make sure that when you do the conjugate of this one, that happens first before you put the negative. It also tells you that they all have to be real numbers. So we're going to determine the values of A, B, and C. First thing I'm going to do is I'm going to state de Moyra's theorem, or de Moyra's. Now, I know I'm saying it wrong, but in my class, we always say de Moyra. So 7 power of n is equal to Rn cis n theta. Now, this is de Moyra's theorem. When we're looking at transposing it to get the roots of unity, remember what we're trying to do here. So if w equals 3, we have 3 roots, which means that here's our unit circle. It's going to look something like this. We're splitting it into 3. We're going to have 3 different values there that, will be our roots of unity. So to work it out, we do the opposite. Now, in de Moyra's theorem, you do r to the power of n. So what's the opposite of doing to the power of n? It's to the third. Oh, sorry. So you flip the fraction that was here originally. So if it's 3, it's going to be 1 over 3, or you can represent that as the third with the 3 out the front. Cis. Now, here it's multiplying by n. So that means that now this time we're going to divide by n. So how many radians are in a full unit circle? It's going to be 2 pi. And to get each time, we're going to multiply it by a number that we're going to call k. So in this case, k is going to be equal to 0, which will be our initial one. Then k will be equal to 1, which will be our next one. And then k will be equal to 2, will be our last one. So to get the roots of unity, I'm going to have to go root 3. Now here it tells us that r is equal to 1. If there was an extra bit here, I would calculate the magnitude of that to get our r value. So 1 to the power of a third, cis 2 pi on 3 times k. So that's going to get us our roots of unity. So now we're going to let k equal 0 to get our very first one. So that's going to be 1, because this part here, 1 to the power of anything is just 1. So 1 cis 2 pi on 3 times 0 is going to be equal to 0. So I'm looking for 1 cos 0 plus 1 sine 0. I. Okay, now this part here on the end, when we think about our unit circle, if I'm looking at where our angle is equal to 0, that is when cos is at positive 1. And that is when our sine value, or the y value, is at 0. So that's our first one. Next one, we're going to let k equal 1. So that's going to be equal to, again, 1 cis 2 pi on 3 times 1. 2 pi on 3 is over here in this quadrant, meaning that sine is going to be positive and cos is going to be negative. So I'm going to use my hand trick to work it out. It's on 3, so we're looking at 60 degrees. So I want to get first cos of 60 degrees. Put down your finger for 60 degrees, and I end up with a half. Remember, cos is in the negative direction. And for sine, I end up with root 3 on 2i, and that's in the positive direction. Next thing we're going to do is we're going to let k equal 2. So 1 didn't change, cis 2 pi on 3 times 2, which is going to be 4 pi on 3. So all the way to here is 3 pi on 3, so 4 pi on 3 must be down here, meaning that cos is going to be negative because it's referring to this axis, still negative, and sine this time is also going to be negative. So cos, rub that out. So it's going to be negative a half minus root 3 on 2i. Okay, so now we've determined all of the roots of unity, but we have to satisfy this part. So when I'm going through, I'm looking at my solutions. This one here, is it greater than 0? No. So my imaginary component here is 0 exactly, so that's not it. This one here, is my imaginary component greater than 0? Yes, it is. So that could be one of them. Next one here, is my imaginary component greater than 0? No, it's not. It's a negative number. So that means that, therefore, w, the root that we were looking for, is minus a half plus root 3 on 2i. Okay, so next thing we're going to do now is read the rest of the question. So if that's our polynomial and it has these roots, so we're going to determine the roots. Or should I say, sorry, the factors. So remember that when we're looking at like a parabola, you probably remember this, but if I have a root here and here, let's say that that number is just a and this one over here is b. If I have those two as the roots of the equation, I had them like this as factors in the equation. So as a factor, it'll be minus whatever that root is. So when I'm determining the factors, it tells me that 1 is a factor, therefore I have to do z minus 1. Then it tells me that minus w is a factor, so I have to do z minus w. So that's going to be this one down here, minus a half plus root 3 on 2i. Then I have to do bracket z minus, and then this one, minus our number, minus 3 on 2i. And this one has the conjugate. Now, the conjugate is the more dominant thing here, so that happens first. What the conjugate is going to do, it's going to change this plus into a minus sign. So I'm just going to write that underneath here to save myself a line of working because, you know, that's life. Okay, so we end up with pz is equal to z minus 1 then we have z, this will turn into a plus, so it'll be minus a half plus root 3 on 2i. Then it'll be z, this will turn into a minus here, so then this will be a plus, so it'll be z minus a half minus root 3 on 2i. Now, you can do that in more steps. I know initially when I tried this problem, I did the factors first, so I did this part simplified, and then I subtracted my answer. I'm just doing this for time in the video, so if you want to take longer, do more steps of working, you definitely can. Okay, so we found our factors, but it's not in the form that we want. We need it to be in expanded form so that we can work out what we have and what we want. Pz equals. Now, to start off with, I'm not going to touch the first bracket at all. Now, you might decide that you want to expand through this, or skip through this part of the video with all the expanding. The QCAA Worked Solutions has got a much faster way of doing it, but I really think that majority of you guys will go through by just expanding the brackets old school way. So we're going to start with that. This term multiplied by that term makes that. This term multiplied by that term makes minus a half z. Z times this makes minus root 3 on 2zi. It's important to take your time with this because otherwise you'll make a mistake here and it'll carry forward and it'll take you forever. So this one times that one, minus a half z. This one times that one plus a quarter. Remember, with your fractions, when you have a half multiplying a half, your numerators multiply, so 1 times 1, and then your denominators multiply. Okay, so that was that one times that one. Now this one times this one, plus root 3 on 4i. Okay, so now we're up to the last term in this. This one times this one. This one times that one. And this one times that one. Now, when we do this final term, root 3 times root 3 will just make regular old 3. And 2 times 2 will make 4. I times I will make I squared, which we know is -1. So don't forget to do that, or that's where your mistake will be. Okay, so give me 1 second to put the charger on. Okay, so now we're going to group together our like terms. So I'm going to start by writing out that first bracket. Nothing happened there. Nothing happens to this first term. Now here, I'm going to comb through. I'm going to look for all of the real components of z. So there's that one, and there's that one, and that's all the real ones that we have. So a half plus a half makes 1. So it's minus z. Write that out, make that clearer. Okay, next one. We're going to look for the imaginary components of z. So we've got this one, and we've got this one. Now we've got a positive and a negative term of that, so they're going to cancel out, so I don't have to worry about them. Okay, next thing we're going to look for is the real components of just the ones. So there's that one and that one. So when I add them together, a quarter plus, remember this will become positive, so it'll be plus 3 on 4, that makes 1, so plus 1. Okay, and lucky last, we're going to simplify the imaginary components, and they will cancel out to 0. Okay, so now you can see this has turned into a much nicer equation. So I can go through and simplify this by just doing this one times this one, makes that, this times this makes that, this times this makes that, this times this, this times that. Wait, almost missed one. And this one times that one. It's a good idea to start writing z's with a line through it so that you can make sure you're not getting them confused with the number 2. Okay, so now when I simplify my final term, I can see that I've cleaned up my expression nicely, and this is what I'm left with. So if we look back at the original question, it tells you here that we're looking for the values of A, B, and C. In our case here, A is the term in front of z to the power of 2. So A equals -2, B equals 2, and C equals -1. Now, if you were looking at how the QCAA has decided to simplify, I'm going to talk about it from this expression here. So they have done all the same steps as me up until this point. Now, their way of simplifying it, which really is quite nice, they've put brackets around this, they've put brackets around that, and then they have done this bracket times that bracket. So when they did that, all they did was they went, okay, our expression looks like this. So this times that, well, we can just say that it's something multiplied by itself. So it's going to be squared. Then this one times that one will make minus root 3 on 2zi. Root 3 on 2i minus a half. Then when they did this times that, it cancels out that middle term. So those two bits in the middle cancel, and then you're just left with this on the end times that on the end. So I'll write this down here. That times that will make minus 3 on 4i. So their expression that they end up with the end looks like this. Okay, and then they worked forward from that point. So once they had this part here, that was squared with the i's, and then, yeah, that's why it worked out so nicely. The squared with the I will turn this into a positive term, and then they followed through with the same steps as me, just expanding normally from there. So potato, potato, do what you want.